Hello, everyone. Welcome. We're happy to have Joel Lewis here today, who will tell us about the combinatorics of q-analogues. And how would you like people to ask questions?
Yeah, so maybe it's a big enough group that maybe the easiest thing is the chat, but if people want to unmute themselves and and talk, that is also totally fine with me. So I'm pretty flexible about that. What works best?
Yeah, all that's fine for me.
Okay.
Yeah, go ahead.
Okay, yeah. So thanks, Simon, for the invitation. Greetings, everyone. I have heard lots about the Euler circle over the years, but I've never been here in person or whatever digitally in person. I'm if you have questions at any point or comments at any point during the talk, please do put something in the chat or shout out. And maybe I'll have some questions for you along the way. So I'm a little bit about me. I'm a combinatorialist. I like enumerative and algebraic combinatorics. And so one thing that means is that it means I like permutations. So for today, for me, a permutation is just a sequence that contains the numbers 1 to n, each exactly once, and so these differ just in the order, in the rearrangement. And Sn is what I'll call the set of all permutations of size n, the symmetric group. So for example, here is S3. Each of its elements is a list of length 3 containing the numbers 1, 2, and 3, and they differ only in the order. And for permutations, even though it's like technically a sequence, I don't usually write the parentheses and the commas. So I just like concatenate things and write it as a. So that's S3. So, okay, I said I'm an enumerative combinatorialist. So what that means is that I like to count things. Well, okay, so like S3, there it is. You can count, and there are 6 of them. And that's like not an interesting kind of counting. The interesting kind of counting is like more general. So yeah, the interesting question is like, how big is Sn in terms of n? And yeah, I see somebody has tossed into the chat that it's n factorial, and let's just think about why that is. I mean, there are many ways maybe to prove this, but one of them is just to think about building a permutation sort of entry by entry, starting from the first entry. And so, you're going to put something in the first position, and that could be any of the n elements. And then after you have chosen the first element, there are like n minus 1 choices for who the second element could be. And like importantly, that's n minus 1 independent of the choice that you made. Right? So like it doesn't matter what you put in the first position, no matter what it was, there are n minus 1 choices for the second. And then having selected the first 2, there are n minus 2 choices for the third, and so on. And finally, for the next to last one, there are n minus 2 choices. And for the next to last one, there are 2 choices, and for the very last one, there's just 1 choice. And then there's a theorem that doesn't really have a name, but I've heard it sort of jokingly called the fundamental theorem of enumerative combinatorics. It says that when you have independent choices like that, the total number of choices you just multiply. So you get n factorial. Great. If anyone's unhappy or has any questions at any point, again, please, you are invited to say so. If you want to turn on your videos, it's like really nicer to talk to like people whose faces you can see. No obligation, but I got a setup where I would actually be able to see you. So like that you can give me thumbs up or roll your eyes at me or whatever is a situationally appropriate. Okay. Okay, so counting permutations. Fine. Well, that wasn't terribly hard. So anytime you can count something, you can try to do more. And so there are different things that could mean, but one thing it could mean is you could try to refine the count by introducing a statistic. And so, for example, permutations, there's a very natural statistic called the inversion number. And what an inversion is, in a permutation, it's just a pair of entries where the bigger one comes before the smaller one. So like 1, 2, 3, the numbers are in their natural increasing order, so there are no inversions. But in like 2, 3, 1, the 2 and the 1 are out of order, and the 3 and the 1 are out of order. So there are 2 inversions in 2, 3, 1. In 3, 2, 1, all 3 pairs of entries are out of order, so there are 3 inversions in 3, 2, 1. And so then, the refined question that you could ask is like, how many permutations are there with k inversions? There's a sort of nice way that combinatorialists like to record that information, and it's called a generating function. And what you do is you like sum up. So you take the sum over all of the objects that you have, so all of the permutations. Q squared plus q squared plus q cubed. And so you get this polynomial, and the coefficients 1, 2, 2, 1 tell you how many permutations there are with each number of inversions. So there's like 1 permutation with 0 inversions, and 2 permutations with 1 inversion in S3, and 2 with 2 inversions, and 1 with 3 inversions. So this is like, this polynomial sort of captures this very refined counting. It tells you for each number of inversions how many permutations are there with that number of inversions. And people use this phrase q-analog, and like, what does that mean? Well, I mean, maybe it sort of means when you plug in q equals 1, you get back the original counting problem, right? Because when you plug in q equals 1 on the left-hand side, you're just adding up for every element in your set 1. So that just gives you the size of the set on the left-hand side. And then the right-hand side, when you plug in q equals 1, well, you'll get the size of the set, in this case 6. How's that? Questions? You okay?
So in this
Yeah.
polynomial, the coefficients here are the number of like elements with that property, right? And q to the power of the inversion number is like the power, if I'm correct.
Yeah, that's right. So if you wanted to know like if you wanted to read off from this polynomial, how many permutations are there with 2 inversions? Well, like for every permutation with 2 inversions, you would pick up a q squared in the sum. And so the coefficient on q squared is the number of the permutations that had exactly 2 inversions. So in this case, that's like 2, 3, 1, and 3, 1, 2. So the coefficient on q to the k is the number of permutations with exactly k inversions. Yeah, for each k. So it sort of packages all that information into a single compact. Yeah, thanks. Okay, so again, this is the answer for S3, but really, we would like not just to know it for S3, but to say for any n, what is this sum? The number, the generating function for permutations by inversions. So like these numbers that tell you in Sn how many permutations are there with k inversions. And so I want to propose that we try to do exactly the same thing that we just did, right? So like let's think about what the first entry of the permutation could be, right? So that was the first step of the previous counting. We're like, okay, well, let's consider who the first entry is, how many choices. Well, now then which choice you make matters, right? Because if you put 1 at the beginning, like that 1 will be sort of involved in 0 inversions, right? Like it's smaller than everything that comes after it, so it doesn't sort of create any inversions. But if you put 2 at the beginning, well, then 1 has to come somewhere later in the permutation. So no matter what, you're going to get 1 inversion by putting 2 at the beginning. And then you'll probably get some more later on. But there will be one of them that involves this 2 at the front. And if you put 17 at the front, then you're guaranteeing me that there will be 16 inversions, right? Because somewhere later, the numbers 1 to 16 all appear, and those will all create an inversion with 17, because 17 is bigger than them, but it will be before. So you could sort of start, and if you just think, so you think about that first entry, and in general, if you put a number r as the first entry of your permutation, that creates, just by doing that, you create r minus 1 inversions with each of between that number r and then each of the numbers 1 through r minus 1. So the first entry of the permutation sort of contributes this number to the number of inversions, right? So like a q to the 0 if you put the 1 first, or disjoint a q to the 1 if you put a 2 first, and so on, and then all the way at the end, if you put the largest number n first, that will create n minus 1 inversions. So you get this sum of powers of q for the number of inversions involving the first entry. Okay, well, now go on, right? So pick up first entry. And now, okay, so we picked 4. So we've got 3 inversions that we know about already for us, right? 4 bigger than 1 and before it, 4 bigger than 2 and before it, 4 bigger than 3 and before it. And now let's think about what happens as we choose the second entry, right? So here are some possible choices for the second entry. So if I put, let's do this one. If I put 6 as the second entry, how many new inversions does that tell me about? Yeah, great. So there are 5 numbers that are smaller than 6, but one of them is the 4 that we already put at the beginning. So like that 6, that will create inversions with 1 and 2 and 3 and 5 are sort of like larger numbers, sorry, are smaller numbers that now will come after. So you get like an extra 4 inversions from putting 6 in the second position. What if you were to put, let's just go up. What if you were to put 5 in the second position? How many inversions would that create on top of this 4 that you had, on top of the 3 inversions that you created by putting the 4 first? Yeah, great. So now you lose the inversion between 5 and 6 that you created if you put 6 there, but you have 5 bigger than 1, 5 bigger than 2, and 5 bigger than 3. Okay, what if we put 3 in the second position? So there's a tiny bit of ambiguity here about like what exactly do I mean? Because the 3 is involved in 3 inversions, one of them with the 4, and then 2 later ones with the 1 and 2. But I've already counted the one with the 4. So what Sheetage, sorry, apologies for that pronunciation, said, and yeah, so it's going to be 2 new inversions that you get, the 3 before the 1 and the 3 before the 2, because the one with the inversion with the 4 we've already taken care of, and similarly the 2, if you put a 2 there, it only creates 1 new inversion, and if you put a 1 there, it doesn't create any new inversions. And so this, like when you put this 4 here, when you put the second entry there, you could create 0 new inversions, 1 new inversion, 2 new inversions, all the way up to, if you put the largest remaining entry in the second position, you could create n minus 2 new inversions between it and like all of the n minus 2 things that will have to come after. And what's nice about this is that, okay, we did this with the first entry 4, but in fact the same, so okay, and we got this contribution from the second entry of q to the 0, 1 plus q squared up to q to the n minus 2. But the nice thing about this is that actually the fact that we put 4 at the beginning is irrelevant. If you had put 17 at the beginning, you would still get the same contribution from the second entry. And if you put anything else in the first position, you would still get the same contribution from the second entry, independent of the contribution that you got from the first entry. And in general, if you've already chosen like k minus 1 entries, those force some number of inversions on you. But now as you pick the kth entry from the left, that can create either 0 or 1 or 2 or all the way up to n minus k new inversions with the stuff that follows it. And that's independent of what you put at the beginning. I mean, it will be involved in some number of inversions with those, but you have already counted that contribution separately. So for each k, you get this contribution that is the sum of the first few powers of q, starting from q to the 0. And again, all of these choices are independent. And so the same principle applies, that if you want to keep track of the total contribution here, you just need to multiply the separate contributions because they are independent of each other. The contribution from each entry doesn't depend on the choices that you made earlier. And so you get this product. And this product is called the q analog of n factorial. And it has this sort of very natural product form that looks just like n times n minus 1 times so on down to 1, except that like each integer k has been replaced by the sum of powers of q. And in fact, there's a notation that's very common in this area, which is that sum. So when we take like 1 plus q squared up to q to the k minus 1, so the first k powers of q, okay, or you could write it as a rational function, wanted to, that sum, people denote it with this notation. You put the integer k in square brackets and a little subscript q for the, and we call that the q number k. I didn't invent any of this language. I promise it's a good language, but it's what people say. All right, so the q number k, and then that product that we had just looks like this: the q number n times the q number n minus 1, and so on, down to the q number 1. And these q numbers have the property that when you plug in q equals 1, you get back the right thing. You get back the integer. And so you get back right away the n factorial that we had before from this one. Questions? Okay. So this is one way you could refine that original question. Let me tell you another way that we could refine the question. So this is a thing I said at the beginning, that a permutation is a sequence that contains numbers 1 to n exactly. That was a dirty lie. That's not what a permutation is today. Today, a permutation is actually a permutation matrix. So what is a permutation matrix of size n? So it's an n by n matrix, an n by n square array that contains a single 1 in every row and column, and all other entries are 0. And there's a simple correspondence between permutation matrices and permutations as words, which is just like, you know, the permutation 2, 3, 1, you can make a matrix out of it. Like in the first row, you put the 1 in the second entry because the first number is 2. And in the second row, you put the 1 in the third entry because the second entry is 3. And in the third row, you put the 1 in the third entry because say that again. Third row, you put the 1 in the first entry. Third row, first entry, because the third element of your permutation is 1. There are like other ways you could do this. There are like at least 8 different conventions that you could use, but this is the one I'm gonna use. Hopefully, I screwed up my slides. It's consistent. So this is like the matrix of the permutation 2, 3, 1. This is the matrix of the permutation 3, 1, 2. How far do you have to read over? So that's what a permutation is going to be for the rest of this talk, is a permutation matrix. And why would you bother transforming a perfectly good language into this other obviously equivalent language? Well, one answer is that when you draw things in this way, it opens up a new perspective, right? You can now think about permutations in a sort of geometric way, as like arrangements of ones in a square grid, satisfying certain conditions, that there's only one, there's exactly one in each row and column. And then you can ask sort of geometrically inspired questions, like suppose that some of the squares of this grid are poisonous and you can't put the ones there. How many ways then can you make a permutation? So this is some other kind of refinement of our original question, where now I'm giving you a board, a subset of the square, and asking just about permutations that are supported on that. One's all fit on that board. So here's a nice board. So the gray squares, those are forbidden. So how many size 5 permutations fit on this board, do we think? Okay, so the total number of size 5 permutations is 5 factorial, which is 120. So I do not think that it could be that there are 200 that fit on this. Yeah. Yeah, all right, this is sort of a trick question. Sorry. Yeah, I mean, there are 0 because, for example, in the first row, you have to have the 1 in either the first column or the second column. In the second row, you have to have the 1 in either the first column or the second column. And then the third row, you're stuck. You've already occupied those 2 columns. So there's nothing you can do. So there's no way you can do this. All right. How about this one? This one, there are permutations. That's a great wrong answer. Yeah, it's a great wrong answer. It's a 2 to the 4 because there are sort of like 2 choices in the first row and 2 choices in the second row, but there aren't really 2 choices in the second row. I mean, not after you've chosen the thing in the first row, right? After you've chosen the thing in the first row, there's actually only 1 choice in the second row left anymore. Yeah, so in fact, there are 4 of them. So here they are. And this, when you're thinking about things this way, there's this other name that people give to this problem. They call them Rook placements, and this comes from recreational mathematics. That people, that there are sort of natural enumerative questions you can ask about, like arranging chess pieces, and one of them is like, what if you want the pieces not to attack each other? Well, for rooks, that means rooks. I don't know if everybody, you're Simon's students, so you should all know things about chess. That rooks attack everything in their row and everything in their column. So the condition non-attacking rooks is exactly the same as the permutation matrix condition, only 1 in any row or column. And so here are the four permutation matrices represented as rook placements of 4 non-attacking rooks, except we don't usually say the word non-attacking. Okay, so in general, if I just give you so if I like throw these gray squares down wherever I want on an n by n square, and I ask you how many rook placements are there on the board, that question is intractable. So there's a technical name for what it means that it's intractable, which is sharp P complete. So this comes from computational complexity theory, but basically subject to conjectures that everyone believes, like the P versus NP problem. No one thinks that you can answer this question efficiently. Like you might be able to answer it more quickly than by brute force checking every single rook placement, but not in any reasonable sort of way. So like if I give you a random 100 by 100 board, there's just no hope of you figuring out exactly how many rook placements there are. So we don't want to study arbitrary boards because we can prove that we can't understand them. But there might be boards that we can understand. And so this is a nice kind of board. It's called a Young diagram of a partition. And so what you do is you give me a sequence of numbers, positive integers, n of them, and that tells me how many white squares there are in each row. So it's like the sequence 4, 3, 3, 2, the partition 4, 3, 3, 2, that's like 4 in the bottom row, 3 in the next row, 3 in the next row, 2 in the top row, and then everything else is forbidden. And this is like everything's left aligned. So so like in particular the case n, that's the whole square. You're just taking all of it, but then I'm letting you sort of take a bite out of the upper right hand corner. Staircase shaped right corner, and then we can ask the same questions that we asked before. Yeah, so sharp P complete. So in computational complexity theory, there are these classes that describe certain kinds of problems. So a sharp P problem is a counting problem where verifying that each element is in the set can be done efficiently. And then a sharp P is like the enumerative problem associated with that. How many are there? And sharp P complete problems are problems that if you could answer those problems efficiently, there's a theorem. If you can answer this problem efficiently, then you could answer all other sharp P problems efficiently. And no one believes that you can answer sharp P enumerative problems efficiently. Like there are lots of examples where people have thought hard about them, and we don't know anything better than like essentially brute force. And so therefore the sharp P complete problems can't be doable, because if they could be, then everything else could be. Yeah, so like in particular, this is like of the same flavor of the P versus NP problem, which is more famous, but in the same spirit, that like computer science can't actually prove that it's hard, but everyone believes that they're hard. Yeah. So okay, so if we wanted to, on this special kind of board though, all right, so in general, it's intractable, but for this nice kind of board, it is not intractable. For this nice kind of board, we can give answers, and this is the answer for this board of this type, of a Young diagram of a partition. You just take the numbers in the partition, you take a product, and like the smallest one, and then the second smallest one -1, and the third smallest one -2, and so on all the way up to the largest minus and -1, and you just multiply. And the proof is do precisely the same thing that we just did in the other two problems. Start putting the rook in the first row and ask how many choices you have, and then go to the second row and ask how many choices you have, and then go to the third row, and so on. And by the time you get to the bottom, you will have used up, n-1 columns, so you'll only have λ1 minus n-1 choices in the bottom. And in fact, it's even better than that, because if you tried to keep track of inversions along the way, you would find that the same argument that we did for inversions also works. And so if you want to count these rook placements on the Young diagram of a partition by numbers of inversions, you just take a product of q numbers, where the q numbers correspond exactly to the numbers that you multiply to get the total number. So this is a wonderful theorem, and the proof is exactly as hard as the two that we just did. You just have to keep track of a little bit more information along the way. So I leave it to you to fill in the details. Okay, so root placements, permutations, gonna abruptly change subject. Before I do that, a quick survey. How many of you have studied some amount of linear algebra? There's like thumbs up things. Okay, and how many of you? Great. Okay, so a bunch of you. How many of you have definitely not studied any linear algebra? Okay, and so then the majority doesn't like responding to questions. That's okay. So it's a mix. So that's good. So I'm gonna tell you a little bit about abstract algebra and linear algebra. And so there will be a moment where I'm gonna say, okay, everybody who doesn't know linear algebra, I'll define this on the next slide. But first, a field. What is a field? So a field is just a set together with some operations in which all of the rules of four-function arithmetic are what you think they are. So what do I mean? I mean, there's an operation addition, and there's an additive inverse identity, additive identity called 0. And there's an operation multiplication, and there's a multiplicative identity called 1. And both of those operations are commutative and associative, and multiplication distributes over addition. And there are inverses you can subtract, and you can divide, except you can't divide by 0 because that leads to paradoxes very quickly. So that's what a field is. And examples of fields that you know and should love are the real numbers, the rational numbers, the complex numbers. Those are all wonderful fields that you probably have at some point and worked with. A thing that you have met and worked with that isn't a field is the integers, and that's right. They're a ring rather than a field. So the problem with the integers is that there are divisions that you can't do inside the integers, right? You can't divide 1 by 2 and have that be meaningful as an integer. It just doesn't agree with the rest of the arithmetic rules. You have to go to a bigger thing, the rational numbers, to be able to do division in the integers. So those are some fields. Simon, do you have anybody doing surreal numbers this group?
There's someone doing Hackenbush, which may relate to surreal numbers here.
Okay, do they know that the surreal numbers are a field?
Then I'm not sure. So
Okay,
I will also be talking about surreal numbers in my combinatorial game theory class in the fall.
Okay, yeah. So there are also lots of other fields. Here's a one that
I guess the surreal numbers are only a field if you use a capital F.
Oh, because of the size thing? Is that what that means? Yeah. Okay. Fair enough. So here's another field that I like as a combinatorialist because it's finite. So like I like counting things. So like counting real numbers gets pretty tricky pretty fast if you want to stay in the finite world. But what you could do is you could take what I'm going to pronounce Z mod PZ. So this is a set whose elements are called 0, 1, up to p minus 1. And the rule for addition, subtraction, and multiplication is that you do those operations just like these are integers. And if you get something that's not in this set, you take modulo p. So you add or subtract multiples of p until you get back into this. So that makes perfect sense whether or not p is prime. That makes perfect sense whether or not p is prime. And what's special when p is prime is that it turns out you can also divide. So for every number in the set other than 0, if p is prime, there's something that you can multiply it by to get 1. So there's a reciprocal. And then you can divide because division is multiplication by the reciprocal. So if p isn't a prime, that fails. Like if you work modulo 6, like there's nothing you can multiply 2 by modulo 6 to get 1. But when for primes, for modulo 7, there is something you can multiply 2 by to get 1 modulo 7. You multiply 2 by 4 and you get 8, but that's 1. So 4 is the inverse, the reciprocal of 2 mod 7. And so then if you want to divide by 2, you just multiply by 4. So these are, so z mod mz for any positive integer m is a ring, but when it's prime, when you're doing it with a prime, you actually get a field. So these are finite fields. So four function arithmetic works, but we only have finitely many numbers in our space. So that's kind of neat. You could ask if there are others. The answer is yes. Here's the complete list. Sort of. Yeah, here's the complete list of this theorem. For each prime power, 2, 4, 8, 16, 3, 9, 27, 81, 5, 125, 25, 126, whatever. Okay, you take every prime and all of its positive powers. There is a field of that size for each of those prime powers. And there's really only one. So like if you write down a field with 125 elements and I write down a field with 125 elements, we might give our elements different names, but there will be a one-to-one correspondence between our elements such that the rules of arithmetic behave the same. So they're just like isomorphic. They're really the same structure. There's like really only morally one field with 125 elements up to calling its elements by different names. And so the field with Q elements where Q is a prime power, we call it FQ. And note that I'm using the same symbol Q to mean something completely different than I was in the first half of the talk. Before it was just a variable with no meaning, and now Q is like a prime power. Okay, finite fields. We all right with this? Yeah, and just a remark, I mean, I'm not going to use this fact in this talk, but if you're wondering, like, okay, I told you how to build the field with 7 elements right there, but what if you wanted the field with 49 elements? Like, you don't take z mod 49z, that's not a field because 49 isn't prime. Instead, you take z mod 7z, and then just like with the complex numbers, you get them from the real numbers by adding this root of a polynomial that didn't have a root. To get z mod, to get f49, you take f7 and you find an appropriate polynomial, and you add a root of that polynomial to z mod 7, and you can get, that's how you get the fields with 49 or 343 or whatever elements, the higher numbers. Okay. Okay, so why did I talk about that? Well, I talked about fields because I want to talk about linear algebra. Because why do I want to talk about linear algebra? I want to talk about linear algebra because permutation matrices are matrices. And if you ask, like, where in mathematics are matrices systematically studied, the answer is that's one of the things that happens in linear algebra. There are more things that happen in linear algebra. That's one thing that happens in the field of linear algebra. So for those of you who have studied linear algebra, maybe you studied it primarily focusing on the rational numbers or the real numbers or the complex numbers. That was certainly true for me, that the first time I met linear algebra, it was exclusively over those fields that I already knew about. But the magic of linear algebra, well, one, there's so much magic in linear algebra. Linear algebra is really magical. I recommend it to you wholeheartedly. But one piece of magic of linear algebra is that almost everything in linear algebra works over every field. So you could do linear algebra over whatever field you want, and basically all the theorems are true in that setting. And so the philosophy of this talk, is that this is just an assertion. I've given you no evidence to believe this philosophy yet. The philosophy of this talk is that if you take prime power q and you take the n by n invertible matrices with entries in the field fq, that is sort of like looking at the permutations of size n. Some sense it's analogous. And the slogan that summarizes this philosophy is that Sn is the group of invertible matrices over the field with one element. The problem with this slogan is there is no such thing as a field with one element, but all right, and then there's something at the bottom of the slide that uses the word categorification, which is a word that I like, but you can read it if you want to read it. I'm not going to say it aloud. So this is the philosophy of this talk. This is the slogan of this talk. So far, you don't have any reason to believe in this philosophy. So what I'd like to do with the rest of my talk is like try to convince you that this philosophy has some merit to it. Now here I included the word invertible matrices, but some of you haven't taken linear algebra, so you don't know what that word means. So let me tell you what it means, but I'm going to tell you what it means in terms of other words that you don't know what they mean. So then I'll tell you what those mean on the next slide. This probably suggests I should have written this talk differently, but it's okay. We'll be all right. So what is an invertible matrix? Here are 3 different definitions of what it means to be an invertible matrix. So the first one, there's an operation, this operation that's denoted with a dot called matrix multiplication. I don't want to tell you what it is. It's not just you multiply entry by entry. That's a terrible operation. This is a much better operation. It's much more complicated to say what it is. It is what it is for good reasons, but I'm not going to tell you about it. It's not commutative. It's a weird operation. It's not commutative, but when you look at square matrices, it does have an identity element. So if you multiply this matrix, the matrix that has 1 on the diagonal and 0 everywhere else, by another matrix of the same dimensions, you get back the other matrix. It doesn't change it. So a matrix is invertible if there's another matrix. So M is invertible if there's another matrix N, such that when you multiply M and N, you get the identity. That's just sort of what invertibility means in any context. There's an identity and there's undoing. All right. Or if you know what a determinant is, then you probably know the theorem of linear algebra that a square matrix is invertible if and only if its determinant is non-zero. Well, that's true over F2. Not very useful. What's useful is that another definition of invertible matrix, so there are lots of, like linear algebra is amazing. There are like all these different ways you can characterize things. So the definition that we'll use is that the rows of the matrix are linearly independent. All right. Now, if you haven't taken linear algebra, this is the definition we're going to use. I'll tell you what linearly independent means in a second. All of these properties, the property is a matrix of being invertible. And I'm going to use this horrendous symbol, GLNFQ, for the set of n by n invertible matrices over FQ. And really the thing I just want to observe is that it's a finite set, right? Because we're looking at square matrices with entries in FQ. So like there are only finitely many choices for each entry. So there are only finitely many matrices. So there are only finitely many invertible matrices. So it's a finite set and we can ask enumerative questions about it. How many, blah, 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 and get finite answers. Okay, so invertible matrix is a matrix whose rows are linearly independent. What does that mean? That just means that no row can be written as a sum of multiples of other rows. So there's no redundant way to express. Yeah, that's right. The analogy here is like Sn to GLNFQ. So the size of the permutation should correspond to the size of the matrices. Exactly. So there's no way to write one row as a sum of multiples of any other row. So, for example, looking at this first matrix here. This question is especially for those of you who haven't taken linear algebra yet. So the question is this matrix invertible? So what I really mean is there some row in this matrix that can be written as a sum of multiples of other rows? That would be bad. See one person nodding. Okay, well, you want to start, or you want to start with C? All right, so this one. So I claim this third matrix over F2. So I'm working over the field F2. So that means the elements of the field are 0 and 1. And the only multiples I can take are the 0th multiple and the first multiple. And when I add two things, I reduce it to either 0 or 1 mod 2. So like if you add 1 and 1, you get 0. So this matrix, Pranav says it's not invertible. Why is it not invertible? Yeah, we'll go back and we'll do it. So why is this matrix not invertible? So I want to vote that we should appeal directly to the definition. That not invertible, we should be able to say that some row is a sum of multiples of other rows. Yeah, that's right. So in this matrix, if you add, let's say we add the first row and the third row together, you get 0 plus 1 is 1, 1 plus 1 is 0, and 1 plus 0 is 1. So if you add the first row and the third row, you get the second row. So this matrix is not invertible because of that. Ooh. So this one, not, oh, highlight, no. Right, whatever. It's good. Right. Not invertible. Okay, how about the first matrix? Yeah, the first matrix also not invertible. Why is the first matrix not invertible? Yeah. Sure. Yeah. Yeah, I mean there are lots of ways you could say it, but maybe the easiest is to say, well, if you just take 0 times each of the other rows, well, that's a multiple, and then you add it up and you get the 0. So in fact, any matrix with a row of all zeros cannot be invertible, because you could just take whatever else you have, you take 0 times it, and you add it together, and you get the 0 row. So and of course you're saying twice, but twice is 0 times in the field with 2 elements. You add something twice that's the same as taking 0 times it. So okay, so the second one, the first one also not invertible. And then for the middle one, okay, I mean what I want to say is, like, right now what you could do is you could just, it's a nice small matrix. You could just try all possible combinations here if you wanted to, and convince yourself that no matter what rows you take and what multiples of them you take, you can't get any of the others. Right? That would be enough for our discussion right now. So the middle one is invertible. Okay, that's invertibility. Okay, I still like to count things. I'm also an algebraic combinatorialist, so that's why we're doing some algebra, but I still like to count things. So let's think about, like, how many invertible matrices are there? And I want to propose that we do the same thing that we did before, which is try to build up an invertible matrix row by row, just like we tried to build up a permutation matrix row by row. And so we can think about, like, how many choices are there for the first row of an invertible matrix over FQ. And I want to claim that there are q to the n choices, right? Because there are q elements in your field, there are n entries, and you can take q, you can just, for each entry, you can take q choices. So q to the n total first rows that you could put in an invertible matrix. How do we feel about that? Yes, great. Okay, I'm a dirty liar. Almost any first row is okay, but if I put all zeros, we're doomed already at the very start. If I give you a row of all zeros, then it doesn't matter what I put later. Those things times 0 will give me that first row. So I can't choose the all 0 row. So there aren't q to the n choices. There are actually q to the n minus 1, because the first row can't be all 0. So that's one bad option. All right, but everything else seems okay initially. All right, so let's go on to the second row. So we're going to choose the second row now. We've chosen the first row. It's something non-zero. We're going to choose the second row. So let's think about it. So again, there are q to the n total choices, but some of them are bad, right? Because some of them are multiples of the first row that we've already chosen. how many multiples does that first row have? Good guess. Yeah, q, right. Right. There are q different numbers in your field. And so each one of them could be the multiplier. So like you have your first row, and then you can multiply by any of these q values, and that would be bad. That's a thing you're not allowed for the second row. That includes, by the way, all zeros if you multiplied it by 0. So there are q bad things that the second row is not allowed to be, regardless of what the first row is. So that means there are q to the n minus q good things. Right. Well, once you've chosen the first 2 rows, now for the third row, right, same story. There are q to the n total possibilities, but you have to rule out the things that are sums of multiples of the first 2 things. Okay, and now it's a theorem that I don't want to sort of spend too much time explaining why, but because the first 2 are not, neither one is a multiple of the other, then the number of ways you can do the sums of multiples of both of them, there will be q squared distinct choices there. It's a nice linear algebraic fact. And in fact, in general, okay, so I'm now using a theorem from linear algebra, and my apologies to those of you who haven't taken linear algebra. You just sort of have to believe me here that once you've chosen the first k rows, if they're all so far so good, so none of them is a multiple of any of the others, then the set of things you can get by taking sums of multiples of them has size q to the k, always, regardless of what the specific rows you chose were. And so there are q to the n minus q to the k choices. Yeah, that's right. So that sort of shows there are at most q squared, but then thinking about exactly why you don't get any redundancy is where the theorem of linear algebra comes in. So there are q to the n minus q to the k choices for row k plus 1. And again, there's an independence here, so you just get this product of these numbers for the size of GL. Well, okay, let's just I mean, I look at this is a nice answer on one hand. On the other hand, like it's obviously not sort of written in the simplest possible way. Like there are powers of q all in here that I could sort of collect up front if I wanted to. I'm just doing basic algebra, right? So then it's like q to the n choose 2, this power. And actually all of these is divisible by q minus 1. So I could like factor that out. And if I do that, this q to the n minus 1 over q minus 1, that is the q number n. And q to the n minus 1 minus 1 over q minus 1, that's the q number n minus 1. And so if I do this, I get, this is one way of writing the answer, where this is exactly this polynomial that we had before for permutations by number of inversions. So that's kind of new. All right. Here's another theorem. All the theorems that I've talked about so far are sort of folklore in some sense. Like it would be unrealistic to try and figure out who the first person to write them down was. This is the first theorem where I think I know who the first person to write it down was. It was Jim Haglund in 1998. And he asked this question, same question, but now putting this board thing in. So we're going to do the same sort of thing we did before. For permutation matrices, we're going to put zeros in the upper right-hand corner according to a partition. And we're going to ask how many invertible matrices are there that look like this. And the same argument that we just gave works. And it gives you this answer. So again, it's a product. And like in each case, you have q to some power for the total number of choices for the row minus the bad choices. And so it works out to this thing. And you can again factor out some powers of q and some powers of q minus 1. And what you get is, okay, a q to the n choose 2 times a q minus 1 to the n times this same sum now over the root placements on that Young diagonal partition. And the same proof works. But like really, this raises the question, like, what the heck? Why does this matrix counting problem, which has no permutations in it anywhere, know about the answer to the permutation count? And so let me tell you about that. So there's this theorem in linear algebra. It's called the Bruhat decomposition. And it says that every invertible matrix can be written in exactly one way as a product of the following form. So you take what's called a lower triangular matrix. So that means everything above the main diagonal is all 0. And you multiply it using matrix multiplication by a matrix that looks like this. So you put some permutation here, and then each inversion of the permutation. So like, let's say like 3 is larger than 2 and before it. So that's the 3. There's the one that corresponds to the 3. There's the one that corresponds to the 2. So it's like this is to the northeast of that. And so you can go like in this column and that row, and there's a position there, and we put a free entry there. So that you can, instead of being 0, that could be any element of your field. And so the theorem, the Bruhat decomposition, in this case, what it asserts is that every matrix can be written like this, where you take invertible lower triangular matrix and a permutation matrix that's been like augmented in this way, where for each inversion you get a free entry. And the thing about that, about this representation, is that if you think about how the matrix multiplication works, apologies to those of you who don't know how matrix multiplication works, so you just have to trust me again. If you think about how matrix multiplication works, if this permutation matrix has some zeros in the upper right-hand corner, then when you do this matrix multiplication, those entries will still stay 0. So the permutation, the invertible matrix that you write like this, has its non-zero entries all on B lambda, if and only if the permutation does. And so that means that you can count the invertible matrices on B lambda by which permutation do they correspond to, and the number of invertible lower triangular matrices is this number, because the ones on the diagonal have to be non-zero, so there are q-1 choices for them. The ones below the diagonal can be anything, so there are q choices for them. And then you have inv of w many free entries here that can be whatever you want. So you get a q to the inv of w, and then you have to sum that over all w. So that's how the invertible matrices know about the permutations. So I think this is really have one theorem. I wanted to tell you one theorem that I proved. Okay, that's actually a lie. It's one of my co-authors proved it, but it's in a paper that I'm. So I want to go back, like way at the beginning. I was like, arbitrary boards, impossible to understand. So let me tell you again, arbitrary boards, impossible to understand. Everything we've seen so far was a polynomial in Q. And like, here's this funny looking board with 3 stars in each row and column. So those could be anything. And so the gray squares are the zeros. The forbidden squares are the zeros. And you can ask, like, how many invertible matrices are there that look like this? And the answer, if Q is an odd power of a prime, is this polynomial. But if Q is a power of 2, it's instead this polynomial that differs by this term. So it's a different polynomial. So there's no single polynomial that describes this answer. Like, this function is sort of badly behaved. And for other boards, it can be much, much worse. So there's a technical statement here for, I don't know if any of you know algebraic geometry, but if you, yeah, so there's something funny that like are some primes nice in those? For some boards, there might be a behavior based on like whether the prime is even or odd or something like that. But for arbitrary boards, it's even worse than that. So I think in general, the answer is no. In general, the answer is no. That particular board like tells the difference between 2 and other primes, but like but there's no general phenomenon that some primes are nicer than others. And in general, these counting functions can be horrendously bad, way beyond the sort of like reasonably describable. But there's this wonderful theorem that says that even though both the permutation count and the matrix count can be really hard to understand, they're still always linked together. They're always linked together. So this statement, why do you have to write this statement like this? Because it's not a polynomial. So I can't say and plug in q equals 1, because that doesn't make sense for a function. Like that only makes sense because the functions were polynomial that you could plug in q equals 1. So here this is some mod thing where like you're taking it, you're multiplying it by q minus 1 to the n, and then you're taking it mod q minus 1 to the n plus 1, which is morally sort of like taking q equals 1. And what it says is that the number of these matrices supported on the board is always equivalent to, okay, this power of q times the number of permutations supported on the board. So that somehow the matrix count always knows about the permutation count. Now, I cannot prove this using the previous proof techniques. All the previous theorems had the same proof, basically start from the top and go down. And that definitely cannot be used to prove this case. So we need a totally different kind of argument. There's a little description of it there. If you're taking group theory, that will be meaningful to you. If not, I'm just saying you need some other machinery. But somehow there's this magnificent fact that these matrices, they always know about the permutation count, which I think is really cool. So in other words, this is getting back to that slogan that somehow the permutations are just like the matrices at q equals 1, even though that doesn't make any sense. So I hope that you sort of believe that a little bit. And thanks so much for listening.
Thanks. So are there any questions now?
Can you extend this to other pieces, like maybe like bishops or something, and study
Yeah.
it that way?
Yeah, so that's a great question. So in the first paper that I know of that really sort of systematically studied rook theory, that's what people call it, was a paper by Kaplansky and Reardon in 1946. And towards the end of their paper, they talk about bishops. And the thing about bishops, right? So like bishops, they move diagonally, right? And so if you think, so they only stay on one color square. So for bishops, it's like there are two boards on top of each other, and you should just like separate them out, right? So like the black squares and the white squares separately. And actually, the behavior of bishops if you just sort of like erase all the white squares and just think about the black squares, it looks just like the behavior of rooks on a board that's been rotated 45 degrees. So bishops are wonderful. They actually are secretly, if you understand everything that there is to understand about rooks, then you also understand everything there is to understand about bishops. You just have to rotate it and then maybe you want to consider two copies of the same problem that are sort of overlapping each other but independent. For other pieces, so like knights are like a totally different, knights or kings, we're talking a totally different kind of behavior because they sort of see locally, but you can put a zillion, whatever. It takes a king or a knight a long time to move all the way across a big board. So there's some sort of like very, very different kind of dynamics. There are still interesting questions. I think there are fairly easy sounding questions that are still open. Like if you ask what the largest number of kings you can put on a chessboard is, like a big square chessboard, I think that's not so hard. But if you ask like how many placements are there when you're just a little bit below that maximum number, I think already that gets hard to understand pretty quickly. So like if you want to count placements of kings or placements of knights, probably also, I think those problems get hard fast. There are interesting, the queen's problem, like can you fit n queens on an n by n board, is like not completely obvious because they attack so many squares. And in fact, for small cases, you can't, like for a 2 by 2 board, you cannot put 2 queens on there. But it is provable that you can put n queens on an n by n board. I think that the problem of exactly knowing how many arrangements there are of n queens on an n by n board is probably impossible. But if you wanted to know like precise asymptotics, I believe that is known. So if you wanted to understand that number of placements, I think that is known. So people have thought it's a fun question and a sort of like a nice mix of like recreational but with interesting mathematics that comes out of it as well.
Like, I guess similar to like this talk about like the Q analogs, like what I saw like previously was like you can have like a grid and you're traveling along the grid and eventually you have good and bad paths along the grid and that eventually gives you the Catalan numbers, right? I think it was something similar to that. And I don't know, like the placements of like the ones and the zeros, they kind of felt similar in that sense. I don't know, like if there's some sort of correlation between them. Like, and I guess what I mean is if you can consider like a zero to be like a horizontal movement and one to be like a vertical movement upwards, right? Along like an n by n grid, like is there some sort of like relation there? Because I was thinking like whenever you're looking at some sort of like abstraction like this, how do you go from like you start with a very nice problem, right? It's you're looking at permutations, you're looking at numbers, and then now you start suddenly all the way over out here doing like no like linear algebra, right? With the matrices. And that kind of like transition from um like one problem stage to another equivalent problem stage, like how does that even like how does that happen, I guess? That's what I was kind of wondering.
Yeah. Okay. So there was like a lot in that question. So I think one thing that I like as a mathematician, so like my wife is a biologist, and like fundamentally at the end of the day, like she has to study like the world as it is. Like the questions that are important are just like they're the important questions because we are what we are. And like I have a lot more flexibility. Like I can think that something will be nice and I can explore it and I can decide, actually, no, this is hard. It's ugly. I don't understand it. I don't think anyone is going to understand it. And I can just like not think about it anymore. Like it's, I can change and find something and go look for something that is beautiful and interesting and has connections. So that's part of the answer is like there are like a lot of different things you might try, and like some of them work out and some of them don't, and then you just can forget about the ones that don't have nice connections. It's like one example is if you took matrices, there's this classic combinatorics problem called the derangement problem, which is permutations where you don't put I in position I. And how many ways can you do that? And there's a nice answer. And then you could ask, like, is there a Q version of that? And I think people have tried like a bunch of different things. And some of them work and some of them don't. Here's one that like, here's an example from our paper that like does work, where like the Q version is like almost as nice as the n equals 1 version. And we sort of figured, this is just an accident, really, that this is the one that is nice. But there are lots of nice combinatorial numbers. You mentioned the Catalan numbers. There are also nice ways to get Stirling numbers, which count set partitions or permutations by number of cycles. Out of problems like this, if you take the triangle board, I think you can get Stirling numbers that way. Catalan number, there are many permutation questions that give you Catalan numbers. Do I know a version of this story that gives you the Q Catalan numbers? There are Q analogues of the Catalan numbers that appear for some of these objects. I don't know how to get one from this particular story that I just told you. But yeah. All right. So I hope that was in some sense an answer.
Are there any other questions?
I guess to kind of like expand upon what I was previously asking, are there any like connect like for Q analogs in particular, would you find them useful in other fields like outside of math? Is that or is
Yeah, okay. Yeah, sure. So actually this paper of mine, this is a paper I wrote in grad school with five friends who are also PhD students. So this question, much to my surprise, got cited by a bunch of people who are electrical engineers. And the reason is that communication theory is part of electrical engineering, and they are interested in models where you're sending some piece of information through a channel, and the channel is maybe noisy. So when you send a piece of information, maybe it gets distorted in various ways, and they want to know, can you receive at the end the message, or what percentage of messages can be received, or what can you do to increase the likelihood or to guarantee that the message gets received. And there are different models depending on what medium for what such a transmission could look like. And one model that's related to something called rank metric coding and some other things is a model where the data is a vector, and what you're doing is multiplying it by a matrix. And one model of data loss that some people were studying was that you force some zeros in this matrix. And so they were interested in understanding, like, when you take a pattern of zeros, what are the different, how many invertible matrices are there that look like that? What are the different ranks? So they had this communication model that turned out to be exactly this thing we were studying. And along the way, we had given some algorithms that would allow you to compute these things. And for them, that was quite nice because they wanted like data, they just wanted to like run some numerical experiments, and they weren't interested in proving theorems because they're engineers, not mathematicians. But along the way to proving theorems, we had worked out relatively efficient ways to compute these counts in concrete cases. And that was very useful to them. So that was a funny accident. Like, I didn't have any idea that this would be interesting to anyone outside of mathematics when we did the work. But it turns out that there's this whole community that for which this is, I mean, I don't want to oversell it. This is like one model in a universe of many different models of communication. But okay, yeah. So it turns out this one, yes. Math is sort of funny that can happen.
Are there any other questions? Well, okay, if not, then thanks again, Joel, for a great talk.
Thanks so much for having me. Thanks everybody for listening.